In this video, we're going to look at a test for independence, which is chi-squared distribution. So the first thing we need to know for a test of independence is that a contingency table is a cross-tabulation of n paired observations into categories, and each cell shows the count of observations that fall into the category defined by its row and column heading. For the chi-squared test, our null hypothesis is going to be variable A is independent of variable B, and our alternative hypothesis is variable A is not independent of variable B. So if we fail to reject our H naught, we can say that the variables are independent, and if we reject H naught, then our variables are not independent. Our test statistic for chi-squared is the sum of all of the observed values minus the expected values squared divided by the expected value. And our degrees of freedom are r minus 1 times c minus 1, and r is the number of rows in the contingency table, and c is the number of columns in the contingency table. And our expected value for each cell is E subscript jk is equal to rj times ck divided by n, and this is the row total times the column total divided by n, total number of observations. So now let's take a look at an example, and we're going to do it by hand and we're going to do it with megastats. So our example problem reads, in the TV show Sneak Preview by late Gene Siskel and Robert Ebert, the two Chicago movie critics reviewed the week's new movie releases and then rated them thumbs up, mixed, or thumbs down. These two critics often saw the merits of a movie differently. At the 1% significance level, does the data provide sufficient evidence to conclude that Siskel's rating is independent of Ebert's rating? And we have a contingency table for the problem. First thing I'm going to do is find all my test statistics. So I've given myself a table below to help keep these calculations organized. So we're going to have our observed value for row 1, column 1 was 24. And I got that number by looking at the contingency table. And now my expected value for row 1, column 1 is equal to our row total, which is 45, times our column total, which is 42, divided by the total number of observations, which was 160. And this is equal to 11.8125. And now our test statistic for row 1, column 1 is going to be chi-squared calc is equal to, we're going to have the observed value, which was 24, minus the expected value, which was 11.8125, and we're going to square this and divide it by the expected value, which was 11.8125, and this is equal to 12.7816. And now I'm going to do this for each cell. So this was row 1, column 1 that we took care of, and I'm going to do this for each of the 9 cells. So for row 1, column 2, we're going to have an observed value of 8. Our expected value for row 1, column 2 is equal to the row 1 total, which was 45, times column 2 total, which was 30, and we're going to divide this by 160, and this is equal to 8.4375. And our chi-squared calc for the cell is equal to observed, which is 8, minus 8.4375 squared divided by 8.4375, and this is equal to 0.0227. And for row 1, column 3, our observed was 13. Our expected for row 1, column 3 is equal to row 1 total of 45 times 88 divided by 160, and this is equal to 24.75. And our chi-squared calc value for this cell is equal to 13 minus 24.75 squared divided by 24.75, and this is equal to 5.5783. And now we're going to continue on row 2. So row 2, column 1, our observed value was equal to 8. Our expected value for row 2, column 1 is equal to 32 times 42 divided by 160, and this is equal to 8.4. And for our chi-squared calc value for this cell, we have 8 minus 8.4 squared divided by 8.4, and this is equal to 0.019. And now for row 2, column 2, our observed is equal to 13. Our expected is equal to 32 times 30 divided by 160, and this is equal to 6. And now our chi-squared calc for this cell is equal to 13 minus 6 squared divided by 6, which is equal to 8.1667. For row 2, column 3, our observed value was 11. Our expected value is 32 times 88 divided by 160, and this is equal to 17.6. And then our chi-squared calc is equal to 11 minus 17.6 squared divided by 17.6, and this is equal to 2.475. And now for our last row. And for our last row, column 1, we have an observed value equal to 10. Our expected value is equal to 83 times 42 divided by 160, and this is equal to 21.7875. And our chi-squared calc value is equal to 10 minus 21.7875 squared divided by 21.7875, and this is equal to 6.3773. For row 3, column 2, we have an observed value equal to 9. We have an expected value equal to 83 times 30 divided by 160, which is equal to 15.5625. And now our chi-squared calc value is equal to 9 minus 15.5625 squared divided by 15.5625, and this is equal to 2.7673. And for row 3, column 3, we have an observed value of 64. We have an expected value of 88 times 83 divided by 160, which is equal to 45.64. And our chi-squared calc value is equal to 64 minus 45.64 squared divided by 45.64, and this is equal to 7.3762. And now that we have all the number crunching done, we want to run the hypothesis test. So our null hypothesis is Siskel's ratings are independent of Ebert's ratings Our alternative hypothesis is Siskel's ratings are not independent of Ebert's ratings. For our degrees of freedom, we're going to use C minus 1 times R minus 1. And we had 3 rows and 3 columns, so this is 3 minus 1 times 3 minus 1, which is equal to 2 times 2, or 4. So we have 4 degrees of freedom. So our chi-squared critical value is equal to, we're going to go to our chi-squared distribution table. And it's important to remember using chi-squared that it reads right, which is different than our z-table, which reads left. So we're going to have, so to find our critical value, we're going to go down to 4 degrees of freedom, and we're going to read across to 1% because we're using a 1% significance test, and we find that our critical value is 13.28. And now that we found our critical value, we're going to worry about our calculated value. So chi-squared calc, and we're going to get this calculated value by adding each calculated value from each of our cells. So we're going to add up all of our chi-squared calc values. And when we add up all these calculated values, we get a total of 45.5641. And because our calculated value is greater than our critical value, we're going to reject H naught, which means that we're saying that our alternative hypothesis is correct, which means that Siskel's ratings are not independent of Ebert's ratings. And now let's take a look at how to do this using megastats. So I'm going to go to Excel, and I've already typed in our contingency table, and then I'm going to go to add-ins and then to megastat, and we're going to go down to chi-squared cross-tab, and then we're going to go to contingency table and click on it. And now it's going to ask us to input the range, and we're going to input all of our cells. And now that we have all the cells highlighted, we're going to hit OK. And we can see that we have a chi-squared calculated value of 45.36, which is just slightly different than what we got, and that is due to rounding. So we have 45.36 chi-squared through megastats, and looking at our p-value is 3.35 e to the negative 0.09, which is less than our significance level of 1%, so we would reject H naught, which is what we've done. And that's all for this video on test for independence.